Good morning, everybody, and welcome to this unique event at the Spring Festival, and many thanks to the Englefield Trust for their support of this and for much else of our education programme. It's good to see so many students from Cheam here as well. Now, it may strike you as strange that we're having a talk about the cutting edge of physics. But actually, when you think about it, this festival, we've had two other events on this very stage that are quite connected, and I want to explain why. So Stephen Osborne, the great pianist, gave a lecture here last week about what does music mean, which explored from the perspective of the artist that inquiry into truth expressed through art, through music. Why do we find that as a route into reality, into fundamental meaning? And then we had the Tibetan monks, representatives of a 1,000-year-old tradition of mystical inquiry by stilling the mind, going into inner consciousness to explore reality from the perspective of the mystic. And now we have one of the world's greatest physicists, Tim Palmer, who has spent his life looking at the reality of the physical world. And all these three disciplines, the root of the artist, the root of the mystic, and the root of the scientist, they're deeply creative ways in which humanity looks at ultimate reality. So from that basis, I would like you to welcome Professor Tim Palmer, who is the Royal Society Research Professor of Physics at Oxford University, one of the most distinguished minds in contemporary physics. And he's also a resident of Peasmore, and I've known him since I was 14 years old. So please give a very warm welcome to Tim Palmer. Right. So Tim, this is your latest book, The Primacy of Doubt. And before we talk about that, maybe you can say something about your professional life, because you've been involved in science since you were a kid. I know that, and your career has gone in interesting directions. So maybe you can tell us a little bit about your life and career.
Just to say, it's not only my latest book, it's my only book. I can't actually see the audience terribly well, but if people are anything like my age, they will remember Patrick Moore, the TV astronomer. I don't know, I think I was captivated into science. I'm a bit like Brian May of Queen, the guitarist of Queen, who also became an astrophysicist because of Patrick Moore. And I think he was the one, if anyone, sort of got me started and interested in science. So it's great to have, I guess, Brian Cox as the modern day Patrick Moore. Yes. But it was TV that, captivated me initially, and I don't know, convinced me that was what I wanted to do with my career. I started my research career actually at Oxford, working on black holes and very esoteric problems in science, and how do we bring the theory of gravity, Einstein's theory of gravity, and Schrödinger and Heisenberg's theory of quantum mechanics together. This is still a cutting-edge problem, by the way.
Which we think maybe you've found now some solution to, but we'll come on to that.
We can talk about that. I was lucky to be offered actually a postdoctoral position with Hawking in Cambridge after my PhD, but I decided to change fields. Partly, I think, I did want to do something useful with my life. I mean, it's a little bit self-indulgent, I think, working on things that probably have no real impact on humanity. So I moved into weather and climate, which has been enormously fulfilling. But the last 10 years or so, I've, as you, I think, said in the introduction, I have a slightly unusual position at Oxford where I'm paid by the Royal Society rather than Oxford University. And it's as near as you can get to a blank check. They just say, do what you like, you know. So I've kind of split my time a little bit between continuing with the climate work and then going back to some of these more fundamental questions.
It's a bit like when the Finnish government paid Sibelius an annual grant just to compose. I mean, you are a scientist, but you're also, in a way, an artist who is just being given the freedom to explore.
Yes. And actually, it's even got me interested in the basic question, what is it that makes us creative? How is it we humans are able to do science, to explore things? And in particular, I mean, since this is a music festival, it rather intrigues me whether the mental processes, for example, that Sibelius would have gone through to come up with his symphonies, are they different to the way scientists work? I actually don't, the more I think about this, the more I don't think they are. I think the fundamental processes of creativity are actually almost identical between the arts and the sciences. And the notion that sciences just work in this kind of methodologically deductive, you know, logical way is completely nonsensical. It's not the way it works at all.
And I think in the book you actually drill down into how that two levels of the way the conscious mind works, so that the noisy unconscious mind is often the one with the eureka moment, isn't it?
It is indeed, and I mean, I hope we get onto that, because I feel it's an important, it has kind of ramifications for anyone, and I think you mentioned there are some school children in the audience. It's really important, actually, for how you structure your time, in giving yourself time, as it were, to do nothing, where ideas can just bubble up from nowhere. Perhaps we'll get onto that, because I think it's an important area.
But meanwhile, since you mentioned the climate and weather, I mean, a lot of what you're saying in this book is it's proposing a new way to assemble probabilities as a more accurate way of looking at forecasting. And this began in your work in Reading at the European Weather Research Centre. And now, as we know, when we look at the weather, it says 15% likelihood of rain, or now that was you that created. So maybe talk a little bit about that and how that then led on to other.
Well, I got into the subject in the days, again, perhaps only the more senior people in the audience of my age will remember, but in the days of Michael Fish, I think.
Oh yes,
Michael Fish. And I mean, I've got, Michael Fish is a great guy. I've met him a few times, and I've got nothing against Michael Fish, but he kind of represents if you like, a philosophy where you don't admit to uncertainty. This book is, by the way, I mean, the theme which runs through the whole book is about the science of uncertainty. How do we, how can actually uncertainty make our lives, our predictions, everything better by being, not trying to sweep it under the carpet and pretend it doesn't exist. But that was the way in which, that was the philosophy that admitting to uncertainty, on the weather forecast or something was sort of tantamount to unprofessionalism. Yeah. And of course, Michael Fish famously became very unstuck in October 1987. Yeah. Not only he did, I mean, the Met Office, I mean, the Director General of the Met Office, became very close to resigning because he was under so much. We give you all these millions and you can't even forecast a storm a few hours before it happens.
The biggest storm in a century, wasn't it?
Yeah. And I had become interested in what's called chaos theory, and I think people perhaps are familiar with the concept of the butterfly effect, that, very small things can have big consequences. I guess Gwyneth Paltrow had a movie about it, right?
Yeah.
Is that right? Sliding Doors or something. So the difference between catching that particular tube
Sliding
train
doors,
or not catching it, totally affected the subsequent path of her life.
Yeah.
So in principle, we know that uncertainty can be important. The issue, though, is that most of the time, it actually isn't that important. So most of the time, butterflies flap their wings, and the consequences aren't that important. But just occasionally, they are. And, for example, we're all familiar with the famous is it a poem? I don't know. For want of a
the nail in the horse's
the horseshoe was lost. For want of a shoe, the horse was lost. For want of a horse, the rider was lost. For want of a rider, the battle was lost. For want of the battle, the kingdom was lost. So okay, but most of the time, presumably horses lost horseshoe nails, and the kingdoms didn't collapse. So the issue really was, the science issue was, how can we determine ahead of time when the butterflies are going to be particularly virulent and change the course of things, and when are they not? And that's where actually the mathematics of chaos theory, which I know people don't want to get into and I won't get into, but the mathematics of chaos theory actually can guide you into this. And as you say, it led to the idea of what's called ensemble forecasting, something I certainly,
You pioneered.
Maybe is the right word, I don't know. Which is basically you run your weather forecast model 50 times every time you do a forecast instead of once. And you look at how close or how divergent the forecasts are. Now, I mean, as you say, Mark, this, a consequence of this, which people may curse, if you like, is the fact that when you look at your weather app and you look at particularly rainfall, it gives you a probability of rainfall. And of course, people say, oh, why can't we just know whether it's going to rain or not? But that's unfortunately not the way the science works. Now, one area where this has made a big impact, so where I'm particularly kind of proud, if you like, is not so much in just daily weather, but really extreme weather. And I'm sure people are, familiar in the past when a really intense hurricane or cyclone or something has hit a country, Bangladesh or the Philippines or somewhere. Typically, the aid agencies only go in and give shelter and food and medicine and so on after the event. And of course, after the event, everything's chaos. But their response would have been, well, we just don't have enough funding to go in. Every time there's the weather, the weather forecast says, oh, that this might happen. If we went in every time that said that, we'd run out of money very quickly. We don't have that money. Now they've got these ensemble forecasts. What they do is a very careful kind of cost-benefit analysis to work out what the threshold probability is for them to take what they call anticipatory action. So they say, okay, we've got X amount of money that we can spend on these emergency reliefs. If the probability exceeds 80%, we know we're going to, 2 times out of 10 it won't happen, but we can take that hit, if you like, knowing that 8 out of 10 times it will happen and will have, fantastic benefits for the society.
And this has now become a model of how emergency services operate now around the planet, because they can now factor in much more accurately through your technique.
Yeah. So as I say, I'm saying this because when you curse your weather app for its imprecision, actually this is becoming a vital tool for important decisions on extreme weather.
Let's move therefore into climate change, because this is something, what's great about Tim's work is it's as you say, you didn't just go into the abstract research with Stephen Hawking, which you could have done, but you wanted to be more relevant to the world, and climate change is something I know you're passionately involved with and are one of the leading authorities in that. Maybe you could explain to us how the probabilities are, because I know there's a little bit of uncertainty in whether clouds, for instance, will actually ameliorate some of the disastrous potentials of climate change with carbon emissions. But maybe you could explain how this process of ensemble forecasting has been applied to climate change that we're all now, and how politicians are having to build on these predictions.
Well, we'll do that, but just before we do that, let me just come back to the weather forecast.
Okay.
Because I want people to think about this question. Suppose you were planning, to go for a walk in the countryside tomorrow, or even, this afternoon, let's say, although what I'm about to say I don't think applies to this afternoon, but just suppose you're about to go for a walk in the countryside, you look at your weather app, and it says there's a 40% chance of a heavy shower. So you could potentially pack your raincoat in your backpack or something, but it's a bit heavy and it's a bit of a faff, to have to take it. On the other hand, if you really did get drenched by a heavy shower, it would be extremely uncomfortable for quite a while afterwards. The point is that you, as an individual, have to make that decision. Is it worth the slight inconvenience of packing a raincoat, given a 40% chance? Now, obviously, I can't tell you that, and no scientist is going to be able to tell you that question. It's an individual question.
Yeah, absolutely.
For your own particular circumstances. Now, the same is true for climate change. It does slightly rankle when I hear people say, oh, well, just listen to the scientists, as if the scientists know precisely what the climate's going to be like in 50 years' time. And there are uncertainties about how bad climate change will be in the coming century. It's not because we understand the fact that we're emitting carbon dioxide in the atmosphere. Carbon dioxide's a greenhouse gas. That's kind of a straightforward problem. But there are kind of knock-on consequences which are much harder to estimate. And the one you mentioned is actually quite a good example. It's about clouds. How do the clouds around the Earth respond to these increasing levels of carbon dioxide? Because clouds play a major role in ameliorating the climate. If you have low-level cloud, what we call stratus cloud, it tends to block the sunshine and the surface temperature is relatively cool. If you actually have very high-level, what's called cirrus cloud, way up high in the atmosphere, it tends to be little icy crystals of cloud, that will often stop frost from forming overnight. So high-level cloud actually can warm the planet, low-level cloud can cool the planet. And a question which we don't really know the answer to is actually how clouds, both the high and low-level clouds, will respond. So there is inevitably going to be a range of possible levels of global warming that we should expect in the coming century. We can't say it will be 3 degrees warmer or it will be 4 degrees warmer. We have to give a range. And I kind of feel anyone who is deterministic about this problem, and it could be either Greta Thunberg at one end of the spectrum or a climate denier at the other end of the spectrum, they're both in a way being unscientific. Now the problem then becomes, and this is where again it's not a scientific problem, is for politicians to decide, given the risk of extreme weather, sea level rise, all these things associated with climate change, is it worth changing the economy, spending money on the economy to decarbonize our transport, our industrial processes and heating and so on, or not? And again, I just stress that is not itself a scientific question. No. So scientists can provide and should provide the input, and I feel, as I say, I feel passionately we have to be very politically neutral about this and just say this is the best science we've got. And then the politicians have to decide.
Absolutely.
And the public, of course.
In the book, you use two rather interesting analogies of this. So, for instance, in the weather prediction, if the Queen is coming to your garden party, you're going to think much more carefully about whether you put the marquee up or not, whether it's just your kids and the neighbours. So in that case, you're going to be looking at the probabilities and think, well, actually, we should have a marquee because that's so important. Mm. And that is an example of how maybe the political decision of whether to act or not. And then there's another amusing one, which I hope you'll forgive me for quoting, and this is your colleague Sabine Hosenfelder, and she summarized it quite well when she said, "Science does not tell you not to pee on high-voltage electricity cables. It simply tells you that urine is a good conductor of electricity."
That's absolutely right, and that's why I say, scientists have enormous value for inputting into policy decisions, and of course, as individuals, we have our own decisions. And in the book, I try to, if you like, tell you that my own personal view is it's almost a no-brainer that we should be cutting our emissions. But that's me talking a little bit with my, physicist hat off, and I'm a member of society in general hat on.
Yeah.
And I think the point I'm trying to make is it's important to distinguish them.
Absolutely. So this art of prediction is an art as well as a science.
That's
but
right.
Look, there are other areas that fascinate me that this model applies to that are also extremely relevant to our lives, and particularly recently, because you've applied this to not only weather and climate change, but economics, pandemics, and conflict around the world. So perhaps you could talk through each of those.
The pandemic, let's talk about the pandemic one, because that's actually quite a mature subject now. And of course, COVID gave it the impetus. And I was writing the book pretty much during the COVID spell. So, and that was interesting because the government wanted to know in the early days not only what the most likely number of hospitalizations and deaths from COVID would be for a given policy, either laissez-faire or highly regulated in terms of interaction between people, so highly with a very strong degree of shutdown. Not only did they want to know the most likely outcomes, but they wanted to know a reasonable worst case scenario. And actually most of the decisions that were made in government were actually based on what was considered reasonable worst case scenarios. So that by its nature requires one to
absolutely
to be able to estimate the impact of uncertainties in the models or uncertainties in the data where the models are started from, and so on and so forth. And it turned out that the epidemiological modelers who, they were suddenly faced with really getting up to speed in a very rapidly developing subject, turned to the climate community for advice on how to do this. How do we generate our own probabilistic ensemble forecasts? What are the right parameters to vary? How can we learn from the climate community?
And so this is all through a mathematical program, is it as well?
Sorry?
This is all through a mathematical process.
Exactly, yes. No, that's right. The epidemiological models are highly mathematical. They make assumptions because ultimately they're about how people interact. And the big problem of representing so-called super spreaders, individuals that actually might have massive interactions with people that then become very significant. How do you represent those in the models? But the important point was that there was a kind of real need for an estimate of plausible worst case scenario, which meant having to forecast not just the most likely situation, but the range of possible situations. So really that thrust ensemble forecasting into the fore, and it's become a highly developed field in disease prediction. I did look into, it's always interested me, economics, and not least after the 2008 financial crash.
Yes.
The Queen famously visited the City of London and sort of asked, why didn't we foresee this? And the then...
A bit like the Michael Fish storm.
Well, that's right. So the then chief economist of the Bank of England, a guy called Andy Haldane, made this very famous remark that this 2008 event was their Michael Fish moment. So that got me interested in whether it was possible to apply, again, these same ensemble forecasting ideas into economics. And if you read the chapter in the book, you'll see it's a little bit frustrating because actually the subject hasn't moved on, despite the 2008 situation. But I ended up doing a bit of research, actually. Writing the book actually led to doing a little bit of research with some students and postdocs at Oxford going back onto the 2008 crash.
And could this, in other words, there's something intrinsically unstable about the global economic system that, like the climate change and like the butterfly, it might suddenly...
Exactly. This seems to be a very generic property of lots of systems which we would call non-linear. And in other words, the weather is an example, I think the economy is an example, probably disease is an example, I think conflict's an example. Even actually the motion of planets around the sun, which is surprising perhaps, which is that they can be very periodic and predictable for long periods of time, and they can lull you into a false sense of security about the predictability of the system. But then suddenly they come across a particular set of circumstances where
That was one of the most surprising things in your book, and I went to Tim's lecture at the Royal Institution, which was full of extremely learned scientists, and it was way above my understanding, and my role today is partly to moderate this conversation to the layman here in the room. But what fascinated me there was the way that these planets that seem so beautifully in an elliptical, they can and that the Earth might do that.
It can't be ruled out.
It can't be ruled out.
What is a more plausible situation is, and I'm sure some people are familiar with this, is with asteroids.
Yes.
So asteroids, in a way, they have a sort of manifestation of this unpredictability, and they are much more unpredictable. So whilst I think it is conceivable that the Earth might suddenly be ejected from the solar system,
let's hope not.
If it happens, there's not much we can do about it. So you can just say your goodbyes and that'll be it. But something we can do something about is to anticipate a possible unpredictable asteroid hitting. It wouldn't destroy Earth, but it could knock out a big city like London. If an asteroid hit London, it could pretty much wipe out. So it was very interesting. I'm sure some people will know that NASA recently sent up a satellite to just see, if it crashed into the asteroid, could it divert it enough? We'll have a certain prediction window. I don't know what that'll be, a year or so, maybe. If we zap the asteroid a year before, can we zap it enough to take it off its path so it doesn't hit
There are
the
lots
Earth?
of Hollywood movies based around those disaster possibilities.
No, but the conclusion was that we can. So I think that we should be kind of happy that that's an area, again, of chaos theory where we can apply science to avoid a catastrophe.
How does this also apply? Because this was something else I was fascinated that in your book, that conflicts around the world are also subject to this chaos theory, where if there's a long border. Tell us a little bit about that, because we're living in a world at the moment where there's so much conflict, and how is that also within this uncertainty paradigm?
The story actually, interestingly, goes right back to the beginning of the 20th century, and a kind of a hero of mine, a chap called Lewis Fry Richardson, who actually literally did the first sort of scientific calculation of a weather forecast. And he did it. He was a Quaker, born into a Quaker family, and he refused to fight in the First World War, but he was sent on ambulance duty to the front. And in his free time, he did the first calculations of the weather, of a weather forecast. I mean, it took him like 6 months to do a 24-hour weather forecast, so it wasn't much use, but it set out the scientific principles. After the war, the Met Office became part of the Ministry of War, and he refused. He refused to carry on belonging to them because of that, and he resigned. And he set his scientific goals on conflict prediction. And one of the he poured through masses of data. What are the factors which cause countries to go to war with each other? And one factor which he discovered was the length of the common border between the two countries. But this had an interesting ramification, an unanticipated one, because he went to different reference books and he discovered that the length of the border, let's say between Spain and Portugal or something, was quoted differently in different sources. And he couldn't figure out why this was initially, because it should be well defined. But then he realized that the length of a border depends on the accuracy with which you measure the border. So if you have a very kind of coarse measuring stick, that's only, let's say 10 miles long, you'll get one value. If you have a measuring stick that's 1 mile long, you'll get a larger value. If you have a measuring stick that's 10 meters long, you might get an even larger
because
value.
of the irregularities of the shape. Right, okay.
And this led to a type of mathematics called fractal mathematics. So the fractals, which really
which
underpin a lot of
chaos.
this book,
Yes.
kind of go back to Richardson and his realization that measuring the length of a border of a country is complicated. And he wrote a paper, How Long is the Coastline of Great Britain? And his basic answer was, it depends on the measuring stick, whether it's a mile long or an inch long or a centimetre. You'll get different numbers. And this is precisely what characterizes a fractal as opposed to a regular kind of curve. And fractals play not only a big role in this book, they play a big role in chaos theory and in my view, maybe the clue to understanding some of the deepest problems in physics.
Well, let's then go into these deepest problems in physics, because again, you're speaking, certainly from my point of view, to the layman here. But I do know that Einstein's relativity and Planck's and others' quantum mechanics haven't yet married up. Can you tell us just briefly summarize what is Einstein's relativity and then what is quantum mechanics and how they are in conflict? Now, be prepared to exercise, but this is
Lock
great.
the doors.
You're not talking to your PhD students at Oxford now, you're talking to a music festival audience. But anyway, I'd love to hear it from you.
Well, okay, so let's go back to the scientific kind of renaissance of Newton. So Newton was the first one to kind of posit a mathematical theory of gravity. And one of the great things it explained was the observations by Kepler and Tycho Brahe. He realized that you can explain all the seemingly complicated motions of the planets by a law of gravity which predicts that these planets move on ellipses with the sun, so at what's called one of the focal points of the ellipse. It's not actually at the center of the ellipse, it's one of the foci of the ellipse. Fantastically successful theory. I mean, science never looked back after that. Until Einstein came along in the early 20th century, and there were some discrepancies, some small discrepancies, and in Newton's theory, particularly about the motion of Mercury, which is the closest planet. And Einstein, completely out of the blue, because this was not an idea that other people were thinking about, he just had it. I mean,
again, through inspiration.
I hope we get to talk about how people have ideas.
We will.
I think this
we
is really
really
important.
will.
Anyway, but he had this
sure
idea that maybe this idea of forces, gravity as a force, isn't right, and that maybe space and space-time, what's called space-time, is actually something that's curved, so that when you shine a light beam from A to B, it doesn't actually go in a completely straight line, but it kind of goes in a slightly curved path. Let's say the gravitational effect of the sun is to slightly distort the what we call the geometry of space-time, and that bends a bit like a rubber sheet, if you like. But okay, so that's one great revolution that happened in the 1915, 1916. Then scientists like Max Planck, famous German scientist, realized there were also things wrong with our understanding of how light that is emitted from a hot body, it didn't fit in with our understanding of light as the 19th century physicists would have it. And this led to the theory of quantum mechanics, mainly by two German scientists. Well, no, one was Austrian actually, Erwin Schrödinger, and German Werner Heisenberg. Again, they came up with a mathematical theory which fitted all the experiments fantastically, but nobody could understand what it really meant because it predicted really weird things. And Schrödinger I mean, Schrödinger was actually himself skeptical that his theory was the right theory, and he came up with his famous, now eponymous cat. So if you don't know what Schrödinger's cat is, the idea is that you have a box which contains a cat, and it also contains an atom which could emit a particle within a certain period of time, and the particle can break a capsule of cyanide, and it would kill the cat if the cyanide capsule was broken. So you go to quantum mechanics and you say, what is the state of the cat after 30 minutes? Is it alive or dead? Mm-hmm. Now, you might say, most people might think quantum mechanics predicts that there is a certain probability for the cat to be alive. You know, you say, well, this atom decays with a probability of 50%, let's say, within 30 minutes. Therefore, there's a certain probability that the cat's alive and a certain probability that the cat's dead. But that's not what quantum mechanics says. This is a bizarre thing. The quantum mechanics actually says the cat is both alive and dead at the same time. Okay, everyone will think this is completely crazy. Can't be. But we spent 100 years almost trying to come up with an alternative where that stupid idea doesn't work, or is replaced by a more sensible idea, like the cat is 30% alive, and in 30%, the obvious answer is in 30% of the occasions where you did the experiment, the cat will be alive, and in 70%, the cat will be dead. Yeah. That's what we would like to happen.
To think. Yeah.
But quantum mechanics resolutely says, no, that's not what it is. The cat is 30% alive and 70% dead at the same time.
And is this also the famous double split where a light behaves either like a wave or like a particle, depending on the observer? The observer becomes part of the system. You can't actually detach yourself from...
Yes.
In the classical Newtonian idea, we're watching this machine, and in quantum mechanics, we are part of the system.
That's right. Now, I just want to come back to the thing that quantum mechanics has passed every single experimental test that's been thrown at it, and it's fantastically accurate. It predicts properties of particles to an accuracy equivalent to measuring the distance between London and New York to the thickness of a human hair.
Wow.
So it's phenomenally accurate. And so the people have been saying, so right from probably the immediate post-war years, post-World War II, people said, okay, we've got Einstein's theory of gravity, we've got quantum mechanics, it's fantastically accurate. We'll just marry the two to kind of produce a theory of gravity where maybe this curvature of space-time has this kind of quantum structure. It's somehow uncertain, but we'll marry the two theories together. And that just has never worked. You know, about 40 years ago maybe, people were very excited by a thing called string theory.
Yeah.
But that's
multiple universe. Is that multiple universes?
It's sort of, it's related to that. But that has not delivered its promise. So we're kind of back to kind of square one. And finally, people are saying, physicists are saying, well, maybe we need to go back to quantum mechanics. Because up till now, you see, if I had been a really absolutely just dyed-in-the-wool mainstream physicist, and you threw all this wave-particle duality at me, my response would be, just get over it, because it works. I have a mathematical theory. Maybe just the way the world works is not how the human brain can comprehend, so get over it.
Yeah.
But finally, people are beginning to say, okay, we've spent 50 or more years trying to bring quantum mechanics and relativity together and have failed, so maybe there is something different. There is something wrong with quantum mechanics. We've got to get to the bottom of it.
And do you believe, Tim, in all, I'm sure, modesty, that your idea now might, by pushing, explain how you think you may have resolved this paradox?
Well, so the Nobel Prize for this year was given to 3 experimental physicists who did an experiment which has been almost universally interpreted in the media as saying, but we didn't actually bother explain, Einstein never would accept quantum mechanics. He famously said God does not play dice.
Yes.
See, when we talk about weather and uncertainty in weather forecasts, it's not because the equations are uncertain, it's because we don't know everything. We don't know all those butterflies are flapping. If we could know all those butterflies, we would actually have perfect knowledge. But the quantum mechanics, the practitioners of quantum mechanics would say that the actual equations are uncertain. It's a kind of a different level. It's not us that's uncertain, but the actual equations are uncertain. Right. Einstein hated that idea. He said, God does not play dice. That's his famous quote to that idea that the equations are uncertain. All right, so there is an experiment that was done, actually continuously over several decades, which won 3 experimental physicists from different places around the world the Nobel Prize. And it's a thing called the Bell experiment. We don't have to. Bell is an Irish physicist who proposed this thing. Sadly died some years back. And what this experiment seems to show is that, well, first of all, it shows that it seems to show Einstein was wrong in the sense that you either have to believe that the laws of physics really are indeterministic, so there's some kind of randomness in the equations, or you have to believe in something else which Einstein equally hated, which he called spooky action at a distance. And spooky action at a distance means that something that you do today, whether you keep your hand on the chair or raise it up, there you go. So you doing that, yes, if you believe in spooky action at a distance, has had an effect on somebody else sitting on a chair, maybe in a different galaxy. I mean, that's kind of
instantaneous
kind of transmission.
Than the speed of light.
Faster than the speed of light. That's also crazy. But the conventional explanation of these experiments, which won these 3 physicists the Nobel Prize, is that it's one or the other. You either have to have indeterminism or spooky action at a distance. And Einstein hated both of them. Yeah. So ergo, he was wrong, at least in one respect. However, now I don't, who am I? But I don't believe that those actually are the only 2 possibilities. And there's a third one, which I think would appeal to somebody. I think it probably appeals to you, Mark, but certainly somebody musical, I think it would appeal to. And I'll try to explain why I believe that. Please. Because when you learn science in school, I mean, you learn particular, Newton's laws of motion, and they predict, if you throw a projectile up in the air, predict where it'll land. That's fine. And then you say, well, okay, what's the cricket ball? It says a cricket ball. What's the cricket ball made of? And okay, we've understood objects like cricket balls because they're made of atoms, and we have equations for understanding how those atoms behave. And then you say, okay, what's atoms? What are atoms made from? And we now know they're made from electrons and protons and neutrons, and now we have theories which describe how individual protons and neutrons and electrons.
We're getting reductionist.
So we're going
smaller and smaller.
We're following this sort of philosophy that to understand the world better and better, we need to probe smaller and smaller scales.
Hence the Hadron Collider.
Yeah, the Large Hadron Collider is the ultimate embodiment of that, because it accelerates particles to such a speed that when they collide, they really probe so even the protons, they get split apart into quarks, which are the sort of constituents of protons. So the way physics has gone, science indeed, is this kind of somewhat reductionist program that to understand our world better and better, we've got to get to smaller and smaller scales and develop equations for how those smaller and smaller scales work. But there's another possibility, and this is why I'm interested in this Bell experiment, because it's a possibility that would explain the Bell experiment without needing either spooky action at a distance or this God playing dice sort of thing, which is actually that the fundamental laws of physics may ultimately reflect the structure of the universe as a whole, rather than just, you see, the most physicists, again, if I put my conventional physics hat on, and they would say, oh yeah, but how do we explain Beethoven's Fifth Symphony and all the wonderful things that humans produce? They will say, well, okay, well, that's just an emergent feature of these laws on the very small scales. Once we stick enough small-scale stuff together, wonderful things will happen, and Beethoven's Fifth will emerge out of that. So that might be wrong. And the laws of physics at their most fundamental may actually reflect structure for the universe as a
holistic approach.
It would be much more holistic. Now, whether this idea is right or not, I don't know for sure, obviously, but what I am pretty confident about is that it provides a third explanation of this result which got the Nobel Prize winners their prize, which doesn't require either of the things which Einstein felt were abhorrent about physics. So I'm inclined to take it seriously, and I think, it would certainly give us a very different perspective on how we should go about. I'll just say one last thing, Mark, and I'll pass over to you. Give a very different perspective on how the laws of physics should be formulated. And I should just say that part of my inspiration for this came from thinking about these chaotic systems, things like, weather chaos and so on. Because when you take the equations of weather systems, simplify them but keep the essential ingredients of chaos, and look at how they have a holistic structure. They trace out a type of geometry which actually involves these fractals in what's called state space. That's a kind of a hint of it. So you see holistic structures emerging from chaotic equations. And that has very much been my inspiration for thinking about these much kind of more fundamental questions about the nature of quantum physics and its role in the universe. So it has motivation from chaos theory. I think it's plausible, but we'll need the experiments ultimately to show whether it's the right idea.
But from my perspective, as someone who's more leaning towards the artistic and the mystical side, I just want to remind us all, and maybe you can comment, Max Planck, who was one of the Nobel Prize-winning scientists that formulated quantum mechanics. He said, I regard consciousness as fundamental. I regard matter as derivative from consciousness. We cannot get behind consciousness. And this has suggested to some other people who are more mystically inclined that the universe, rather than being a great physical machine, is a huge thought, in fact a divine thought of which we are all an aspect. So and this fits in with the Tibetan Buddhist idea. It fits in with what I experience when I'm listening to music at the highest sublime level. I feel that these composers are moving their consciousness into something far, far, far greater, and that when the performance is wonderful and we join with that we are actually being raised into that universal, sublime, and the Tibetans would say that connects with compassion, with love, with the divine, with eternity. Now, that could be the topic of a huge other thing, and maybe next year we'll look at that, because we've only got 10 minutes left. Well, look, but is there a possibility of that? Because this is Max Planck.
Yeah, I mean, we're straying well beyond the domains of conventional science here. So I have some sympathy with your point of view, but I just want to make a much more pedestrian point in relation to music, because you could say that our conventional view about physics is like trying to drill into a Beethoven symphony and say, okay, to really understand this, I'm going to look in depth at bar number 59, and drill into depth at the use of semiquavers and the particular time signature, without any sense that actually the reason he wrote it was because he had a vision of the whole structure as something which only hangs together once you see the whole thing. And I think, this is my, I don't want to be too dogmatic about this, but I just feel by taking this highly reductionist view of smaller is more fundamental, we're being a bit myopic, and we're missing actually the large picture. So this is, I think, an area where there is certainly some connectivity with the arts, because this is, thinking of analyzing something without taking a vision of the whole structure, doesn't work in music, doesn't work in art, in anything really in the arts and literature. So I think this is a clear.
And also, you posit in the final chapters of your book how this creative process is as applicable to the great breakthroughs in science as in art. What I'd like to remind you and all of us of is what Mozart said, because your idea is that while we're randomly doing something else, then a thought comes to us. Is that right?
I do want to just, if we got 2 minutes, just elaborate on that, because I actually feel that a lot of the new excitement about ChatGPT and things. I mean, it is exciting, but I don't think these are operating like we humans think, and the process by which we are creative. And I mean, one thing that has absolutely fascinated me is how do we humans do what we do with 20 watts of power, enough power to light a light bulb.
Yeah.
When I run a computer model or ChatGPT accesses a data center to do its learning, that data center takes 20 megawatts, 6 orders of magnitude more energy. So there's something fundamentally different. And I think the low energy of our brain actually makes the brain a sort of noisy environment. It's not this kind of completely deterministic structure. And it's the noise which actually is the ultimate origin of the kind of crazy ideas that we get. But we have this duality of thinking. When we go into concentrated mode, we can say, oh yeah, that idea really was stupid. That's a daft idea. Why throw that one away? Or throw that one away. And then suddenly one comes up, oh my God, that is going to be a really useful idea.
Yeah.
And that's not the way ChatGPT works. It just works by analyzing the data that's out there. And I tell my students, and this is why I'm saying to, if there are any students in the audience, I tell my students at Oxford, don't spend every waking moment just staring at your computer screen or focusing hard. You've got to leave an hour or two every day to pretty much do nothing.
Yeah.
And that is the time when creative ideas will bubble up. And if you suppress that, you will never have any creative ideas.
A lot of writers and artists and musicians and physicists go for a walk, and it's when they're going for a walk that things are... But I do want to also just mention what Mozart said, because I think it's similar, but it's slightly different, and it ties in more with this other idea of the universal consciousness. He said everything that he wrote, from Don Giovanni to a minuet, began as a beam of light, and all he had to do was focus on that light, and it came out. Because he didn't constantly change. It was like a printer. Brrr, there it is. So that implies the alternative mystic view, where the artist, and indeed the Tibetan monks would also sort of bring their world of meditation into the same, is accessing something beyond their individual consciousness. But it's not to contradict what you're saying, because this study of consciousness is now, fascinatingly, scientists are looking at these questions which previously were only the realm of the mystic or the artist. And what I think is exciting is that these disciplines are coming together. And I hope within our lifetime they will connect. And
it's finally become pressing because of all the AI developments. We've really got to understand, are we fundamentally the same in terms of what we call intelligence and what we call consciousness as a sophisticated AI program, or are there still fundamental differences? And it's no longer just a matter of idle philosophy. This is
this is very
practical problem.
Current news stories now, and my instinct says that there are fundamental differences, and I think by exploring AI, we will finally maybe realize what is unique about us, which is beyond the merely rational in that way. Now, Tim, thank you very, 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 very much. Before we finish, I'm sure there are hundreds of questions. If you'd like to ask a question, there is a roving mic, and please raise your hand so that our team can bring you the microphone. So.
I was really fascinated to hear some of the things you're talking about, because it's a lot of things I've been thinking about lately. And in particular, I recently read some work by Carlo Rovelli, who a physicist at CERN, and I had an idea. And one of the points that he raised was this idea that what if our model or our understanding of the universe is not just to break things down into particles, but it's also about relationships between things. And one of the points that struck me was that it's possible that there isn't even any physical matter, that everything is in fact to do with interactions of waves, whether they resonate or interfere with each other. And of course that ties into music, because you have harmony and resonance as well.
Yes.
And it kind of struck me, this idea that could possibly be one model for how the universe works in its entirety. I wonder if you could comment on that.
Well, I'm sort of broadly sympathetic to that. I have to sometimes put my hard physics hat on and say, the problem, you can have kind of qualitative ideas. The problem is to come up with a theory which is precise and mathematical and will predict something that can be tested, where you make a different prediction to what quantum mechanics makes. Because that, quantum mechanics has been, despite the fact it's unbelievably weird, almost, I would say, incomprehensible from a sort of philosophical point of view, it nevertheless makes very accurate predictions which have never yet failed. So the test for me and Rovelli and you, if you like, is to be able to encapsulate your ideas into a form where they can be expressed mathematically, and from that can predict an experiment that somebody, perhaps in my lab in Oxford or somewhere else, can do, which would predict A, if your theory is right, and B, if quantum mechanics is right. If the result is A, and it's your theory, then you're on your way to Stockholm or wherever it is.
Another question.
Well, I'd like to say, first of all, thank you very much for a really interesting talk. Like you, I'm an Oxford theoretician of a similar vintage. Probably know many of the same people. I'm reminded in some of your comments about the large-scale nature and potentially also maybe quantum mechanics having some interesting effects of Professor Roger Penrose's views on those topics. Again, another Nobel Prize winner, right, who suggested that perhaps human thought, consciousness and creativity was due to large-scale quantum mechanical effects. I'm wondering what your views might be on that and how that connects with your propositions about changes in quantum mechanics.
Yes. I know Roger very well. And he has a view which is a little bit different perhaps to the one that Max Planck would have had, which, Max Planck viewed consciousness as a kind of fundamental concept that sort of basically defines everything else. Roger's view is that actually quantum mechanics is working deep inside the axons of the neurons in the brain, and actually is a physical process which is actually what makes us conscious beings.
Can I read what...
The short answer is I'm sympathetic, but there are so many aspects. I mean, this is again a problem. It's so difficult to do experiments in the brain where you can probe these ideas. It's just so difficult, how do you even test this idea? So I think we have to say the jury's out on this one.
Let me read you what Sir Roger Penrose, OM FRS, winner of the 2020 Nobel Prize in Physics, says about Tim. The primacy of doubt provides a remarkably broad-ranging account of uncertainty in physics in all its various aspects. I strongly recommend this highly thought-provoking book, which, by the way, you can buy after the talk, and I think that there are some copies for sale when you'll be able to meet the author as well. We have time for one more question. Oh, I'm sure we could be here all afternoon, but who would like to ask?
Thank you. And I'm not sure that the point I want to make is change anything fundamental, but you talked about the economic crash, and as an economist who worked at the New Economics Foundation, I'd like to point out that in 2003, the New Economics Foundation produced a book, The Coming First World Debt Crisis, which was indeed predicting, not, like the weather, I couldn't say when, perhaps, but that it was actually inevitable. And personally, I think the next one is going to be worse. This is going to be a Vicarage Tea Party compared with it.
Mm.
Well, I mean, as I say, I think these what I would call intermittent instabilities, in some sense, are inevitable in all these systems. The question is, to what extent can we control them or, ameliorate them? For example, with climate change, we can, mitigate against them by trying to cut our emissions. Economists will know that part of the reason we had the 2008 crash was the complete deregulation of the financial sectors in the 1990s, and even before that. I suppose it started with Reagan and went on, to Clinton and Blair and so on.
Subprime mortgages had some.
Yeah, I mean that all. So regulation. The regulation that was introduced after the 1930s crash was a way of trying to, make these intermittent instabilities less common, less frequent. But the question really for me is, can economic modelling get to a state of the art where we can make predictions like weather forecasts, where 6 months ahead we can say there is the 30% chance that given the current policies, unless we change direction, we will be facing another crash. And my conclusion is that the kind of conventional types of economic model are not actually suitable for this purpose, but there's an interesting type of model called an agent-based model, which incidentally is used a lot in the COVID modelling world as well, which actually seems to show promise. So I have, again, colleagues in Oxford who work on these agent-based models. So I think there's a chance we'll get there, but who knows.
Thank you very much for your talk. Throughout it, the words doubt, uncertainty, and chaos have been leitmotifs in what you've been saying. And as a non-scientist, I feel very much drawn to things that Mark has been saying. And I would like to suggest that possibly these three words represent a chink in the armor of a scientist, that perhaps doubt and uncertainty and chaos are other words for mystery. Is it possible that there's some element of this in your own thinking, that there's room for individual human feelings, for God perhaps? May I leave it at that?
I mean, I was saying to Mark, I'm not a big fan of the Richard Dawkins sort of view that anyone who has religion is deluded. Because, as you say, there are profound mysteries that we just simply do not know. Actually, it's interesting. Last night, I listened to, I was at a lecture given by a cosmologist in Oxford, and he started his talk with a cartoon. And on the left was a cartoon of a caveman from, let's say, 1 million years ago, looking up at the night sky. And he's saying, what the hell does it all mean? And then on the right was a guy dressed in a white coat with a big telescope behind him, computers wearing away, looking at his computer screen and going, what the hell does it all mean? So there are some fundamental questions that we still, in a way, have made very little progress with. And but I don't think they're outside the scope of science. I think, you know, there are ones, and that's what draws us. You know, what does it all mean? Why is there something rather than nothing? Why do we exist? These are, in principle, science questions that science can ask, but at the moment they are mysteries, and we don't know. And I think we have to face that with some humility, you know, and it's not like Richard Dawkins is suggesting it's all basically tied up, or if it's not tied up, we're very close to tying it up. That's not the case at all.
Well, on that very happy note, may I invite you to show your appreciation to Professor Tim Palmer.